Okay. So, one last day of resonance. I don't think we're going to do resonance. Oh, we will, a little bit. So let's just have a day of it and be done. Let's use resonance explains this. Oh, we didn't really talk about phenols. I'll show you phenol, and then I'm going to show you another cheap way of making it, the industrial way. It's not been on any of our reaction lists up to this point, but phenol's a big deal. Let me show you how they make it industrial. All alcohols have the same pKa. They have a pKa of about 16. 15.7, 15.6, 15.8 seems about normal for an alcohol. But phenol is different. First of all, what does it mean to have a pKa of 10 when the rest of your family has a pKa of 16? What does pKa represent?
The constant for acid dissociation.
Yeah, so Ka is your acid dissociation constant. And then what are the values of Ka? They're either incredibly big or incredibly small. There's such a big variety that doing the P thing to them kind of constrains them. Do we know what the P stands for? Do we know what pH is?
It's the negative log of hydrogen concentration.
pH is the negative log to the base 10 of the H plus concentration. So guess what pKa is?
The negative log.
The negative log to the base 10 of the Ka. So what is Ka?
Acid dissociation.
Acids dissociate, put H plus into solution, and leave the conjugate base. If this is ROH, that's what we're looking at. The ability of an alcohol to dissociate and put H plus into solution. Okay, so we would take the Ka of this, and Ka is always the concentration of products divided by concentration of reactants. But the values of Ka is problematic. They're sometimes huge, times 10 to the 20, sometimes very small, times 10 to the negative 22, times 10 to the negative 50. These are numbers that we don't want to deal with. They're frightening, and the range is too big. So Ka is H plus. This is non-specific here. A minus over the undissociated or free acid. Square brackets means concentration. Okay, so that's your underlying value, and we're we're going to take the log of it to constrain those values down. So what does it mean to be 10 when everything else in your family is 16?
They're less acidic.
Less acidic or more acidic? I don't know. We have a difference of opinion. Okay. Get out calculators. Look at the expression that's on the board. Ka is H plus times A minus divided by HA. As my material gets more acidic, does the value of Ka go up or go down? As HA gets to be more acidic, does Ka go up or does it go down? To be acidic is to put H plus into solution. That means more numerators, less denominators. So Ka goes up as acid goes up. What is negative log, so the base 10 of a Ka that would be equal to 1? When Ka equals 1, I have the same amount of things on the top and the bottom. When log to the base 10, when Ka is 2, what is my value of pKa? You all have calculators. So this is my column for Ka right here, and then this gets to be my column for pKa. But I put a negative here.
Negative 0.301.
All right. What if my value is 10?
One.
Negative 1.
You got a negative there?
Mm-hmm.
Okay. What if my value is 100?
10.
Let's just do. What if my value is 1,000? That 1 is this number of zeros. This 2 is this number of zeros. This 3 is this number of zeros. Okay. What's happening to the value of Ka as my underlying value of pKa? As my value of Ka goes up, what happens to the value of pKa?
It goes down.
It goes down. As Ka goes up, pKa goes down. When Ka changes by a factor of 10, pKa, let's say Ka goes up by 10, pKa goes down by 1 point. When Ka goes up by 100, pKa goes down by 2 digits. When Ka goes up by 1,000, pKa goes down by 3 digits. Okay? We now know everything we need to know. Phenol has a pKa of 10. All the other alcohols out there have a pKa of 16. Tell me about the relative acidity of phenol in comparison to all its other alcohol relatives. Phenol is more acidic. How much more acidic? Phenol has a smaller pKa. Smaller values of pKa means more acidic. Its value of pKa is not 1 notch smaller. It is not 2 notches smaller. It is not 3 notches smaller. It is 6 digits smaller. That one's 16 and that one's 10. How much more acidic is phenol than alcohol?
1 million.
Phenol's 1,000,000 times more acidic than other alcohols. So if I compare, here's an alcohol, and it kind of looks like benzene, only it doesn't have the double bonds. It doesn't have the pi system. It doesn't have the aromatic system. So when it dissociates, it makes this. And nature has decided that you get to do this at about pKa 16. But phenol, when it does the same thing, gets rewarded. That's 1,000,000 times more likely to happen for phenol than it is for cyclohexanol. Cyclohexanol would make cyclohexanoxide and the hydronium ion. And phenol makes phenoxide and the H+. We should explore what it is about phenol that makes that happen. So, resonance explains that all alcohols have pK of about 16, except for phenol. Phenol has a pK of 10, so it's 1,000,000 times more likely. All right, here's what we'll do first. A, draw all contributing resonance structures for cyclohexanol / cyclohex and oxide. Okay. Off you go. Draw them all. How many contributing resonance forms does cyclohexanol have? Well, it depends what semantics. It's either 1 or 0. Because there is no resonance in cyclohexanol. Because the rules for resonance say, take this interesting thing and move it towards the other interesting thing. Take this lone pair of electrons and move it towards the pi bond. Take this negative and move it towards the positive. Take this pi bond and move it towards the positive. And cyclohexanol only has lone pairs of electrons. And they're on the oxygen. There's nothing else to move them to. So A is moot. There's no point in doing it. There isn't anything. Now, so how much resonance stabilization does cyclohexanol have then? None. None at all. So, A, cyclohexanol / cyclohexanoxide has 0 resonance stabilization. Okay, what we're going to do here is B, part 1 and part 2. We're going to draw all the contributing resonance structures for phenol. And then we're going to allow phenol to become phenoxide. And we're going to draw all its resonance structures as well. Off you go. contributing resonance structures are you expecting to draw for phenol? 5. The one in the middle should be symmetrical, with all the pi bonds lined up parallel. If you get to sketch number 3 and all your pi bonds are not parallel and vertical, you're off track. Stop before you make it worse. And go back to the beginning. What is the first thing that we do when we draw a contribute? Our first, after drawing the original molecule, the first structure always
It's a double bond on the substituent.
establishes a double bond between the substituent and the ring. Now, whether that double bond comes from the substituent to the ring or from the ring to the substituent is up to you to figure out. How'd you figure that out?
Because it's multiply bonded or not. So if it's a draw.
Well, this atom, directly attached to the ring, is in possession of lone pairs of electrons, which means this is an electron donating group. And so we have this. And those arrows dead-ended onto an atom, which means that's negative. This oxygen now has 3 bonds, makes it positive. And then we just push that around. My middle sketch has all my pi bonds be parallel, vertical. Plus. If that's what you drew, good. That's correct. Now do phenoxide. Yes, you have to. I know it's a lot of work, but you have to.
Why do you have an arrow going from the phenol to the phenoxide?
Because to get from here to here, I lose this H plus. This is my equilibrium. And to do it this way, I can have them all stacked up on top of each other, because you should still be expecting 5 contributing resonance forms. Organic chemistry students need to learn to write quickly. My professor, Professor Sexton, would write about the count of them, 160 benzene rings in an hour. You had to keep up. So we have all the contributing resonance structures for phenol, and it tells us that I get 5 pictures worth of resonance stabilization for phenol. And I've got all of the contributing resonance structures for phenoxide, and it tells me that I get 5 pictures worth of stabilization for phenoxide. Are my pictures identical to each other? No. They're subtly different from one another, which means one of them has to be better than the other. Which one's better? The top set or the bottom set? Why is the bottom set better?
Makes up the acidity that we're
Start talking, put your hand in front of yourself because you're not super confident. Because what?
because the H plus ions are the ones that are increasing its acidity when it's in equilibrium.
Okay. I hear what you're saying. And that's kind of the outcome. What else have we got? Why is the bottom one better?
It wasn't that good, I just said it had a negative on the oxygen.
Okay. It's not a bad answer.
Would it be more electronegative? That would be a better.
Give the electronegative atom the negative charge. Seems rational. It seems like a good thing. But what else?
There's no positives in the bottom?
There are no positives in the bottom. The bottom has something, and it's, the absence of positives is the key. But it's not just that it doesn't have them, it's that these have both a positive and a negative. These top 3 have a separation of charge. So it's as if every time you write a contributing resonance form, you get money, you get stabilization. But every time you have to separate a charge to make that work, you have to give some of that money back. At the bottom, I have 5 pictures, and there is no separation of charge. On the top, I have 5 pictures, but 3 of them are compromised because they have separated a charge, which means this is more stabilization. So phenol actually benefits from resonance stabilization if it gives away the H. If it gives away the H plus, it ends up gaining stabilization, which is why it's 1,000,000 times more likely to give up that H than a regular alcohol would. Got it? Okay. You need a lot of temperature to make this work. You need kind of industrial temperatures to make this work. I think this would be difficult to do in the lab, but there is an industrial process that you can turn benzene sulfonic acid into phenol by heat treating it. All right, let's ask some more of the same questions. Resonance explains. 2.
Does that mean by the way?
Yes. Amines are bases. They have lone pairs of electrons and they collect hydrogens. Okay. Amines are all bases, and most bases, simple ones, have about the same pKa, except aniline. It is wildly different in its basicity. Figure out why. Aniline would just do the same thing. Right? So what we have to do is what we just did. Only instead of losing an H plus because phenols, alcohols, are mildly acidic. Phenol has a trivial name, it's carbolic acid. Has the word acid in its name. It's more acidic. If I gain proton, I get this. Okay. Draw all the contributing resonance forms for aniline. Aniline also has a lone pair of electrons on the atom that is directly attached to the ring, so will also be an electron donating group. So it will give me 5 contributing resonance structures. These will all count as being activated from that electron donating group. That nitrogen gets a positive charge. My third canonical form is symmetrical. It has all the pi bonds be parallel and vertical, which tells me that I'm on track. Oh, no, that's too much. Okay, those are your contributing resonance structures for aniline. The outside two are perfection because they are identical to one another. The three in the middle are compromised because they have a separation of charge. So I have 5. The more contributing resonance structures I get, the better it is. The more of them that are identical, the better it gets. Any of them that have a separation of charge, you start to detract a little bit. You have to give me some of that stabilization back. So there you go, there's aniline. This is aniline. This gets to be anilinium. Draw all the contributing resonance structures for anilinium. How many contributing resonance structures have we had for aniline? 5. We had for phenol. 5. We had for phenoxide. 5. How many do I get for anilinium? Who has 5? Okay. I think you might supposed to be. How many contributing resonance structures for anilinium have people drawn?
I'm confused if that is a positive or if I'm using the
Yeah, at this point you're supposed to be questioning.
lone pair.
Mm-hmm. Well, look, there's no lone pair. The lone pair got used.
With the other bond.
Make that bond. Lone pair is gone. How many contributing resonance forms do I have for anilinium? That's this one. So I used to have 5 structures contributing to my resonance stabilization. By taking away the lone pair of electrons, I'm down to 2. Does this make anilinium want to be a base? Aniline, want to be a base? No. No, 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 no. By picking up a proton, I lose all of these structures. They're now not available to me. This is resonance stabilization that I was enjoying when I was a proper aromatic molecule. Now, I still got my aromaticity, but I don't get those contributing resonance structures lowering my energy. So this is worse.
So you don't get those because
You've got nowhere to go.
it has 4 bonds and it has a positive.
That nitrogen has 4 bonds. If you think there's a positive right there, so I can take these electrons out of the ring and give them to the nitrogen, that nitrogen would now have 5 bonds. Nitrogen cannot do that. That would be giving 10 electrons to a nitrogen. You just broke the octet rule. Now you are allowed to break the octet rule, but not for nitrogen. Nitrogen won't allow that. So we're stuck. We cannot put anything into or out of the ring, therefore I get what I get. So aniline would lose stabilization if it were a base. So we saw phenol wants to be an acid because of that stabilization. This is the opposite. Aniline does not want to be a base. This is ethanoic acid. It's a regular carboxylic acid. Go ahead and show me the contributing resonance structures for ethanoic acid. Rules for electron delocalization say move a negative towards a positive, move a negative towards a pi bond, move a lone pair of electrons towards a positive, move a lone pair of electrons towards a pi bond, move a pi bond towards a positive, move a pi bond towards a pi bond. So we have something in there. We have a pi bond and a lone pair of electrons. I know which one I'm supposed to move towards the other one. So go do that. my pi bond. If I move my lone pair towards that pi bond, this carbon already has 4 bonds. It's going to lose a bond, has to break a bond. Then it puts that charge on that oxygen. An oxygen with 2 bonds has no charge. An oxygen with 1 bond has a negative. An oxygen with 3 bonds has a positive. Do I have any more contributing resonance structures than this?
Yes.
I do? I'm surprised.
Does the negative move towards the positive?
This one?
Yeah, is that the same thing as the first
Well,
step?
I've drawn that.
Okay.
I've described that already. It's this arrow.
Yeah, never mind.
That's it. I have 1 contributing resonance structure. And I separated a charge. So it's good, but it's not great. All right. Have the acid be an acid. What does it mean to be an acid? Give away the H+. Draw the contributing resonance structures now for acetate. Instead of acetic acid or ethanoic acid, you now have, so this is ethanoic acid, and this is ethanoate. And if you can live with calling this acetic acid, then this gets to be acetate. Without the hydrogen, can you see? Ooh. What have I just done? This is perfect. That is this. These two are the same as each other. And when contributing resonance structures are the same as each other, you get a drop in energy. So this is better. This tells me this material wants to be acidic. It gains stabilization by letting go of the H+. If we did everything for benzoic acid, the atom directly attached to the ring now is multiply bonded to an electronegative atom. So I would be pulling electrons out here. I got that resonance right there. And then I've got all of this resonance as well. So the difference between a regular carboxylic acid that is better when it's deprotonated is even better as a benzoic acid because it doesn't just have these two, it gains 5 additional contributing resonance structures. And the more contributing resonance structures you have, the more stabilization you get. Okay, Wednesday, new topic, we're moving on. There's a little bit hidden still in the aromatic world to do with protecting groups. because the reagents for one reaction might destroy something else that's on the ring, I think I might leave it till later.